Hello everyone, welcome to the free Touch Designer tutorial. I'm Harry. Today, I'll be introducing the application of NVIDIA Fluids in Touch Designer. Let's get started with today's project.
First, let's create a sphere from the SOP family. This sphere will serve as the base particle points for our fluid simulation. Then, in the parameter panel, we need to change the type to polygon. Otherwise, our poly count will become extremely high.
Next, we'll use a transform node to adjust its size. Let's scale it down to 0.04.
Then we'll create an actor, the fundamental component of Touch Designer's physics system. It can be connected to either a bullet solver or an NVIDIA Flex solver, which are the two core solvers we'll be working with.
Next, in the SOP family, let's create a grid and adjust its size to a 16:9 aspect ratio, matching our desired display proportions. Here, we need to set its rows and columns to 250 by 250. This determines the emission points for our sphere particles. Next, we create a null.
We can select the actor and open the instancing in the parameter panel. Then, we drag the null to the translate up.
Next, we select P0. We'll need to wait a moment here as it processes the calculations.
We continue to choose P1 and P2.
This way, our spheres will be distributed in a 250 by 250 rectangular grid as intended.
First, we select an actor and click Initialize.
Now we can see how our particles are arranged within the actor.
We can click plus to activate the actor, and if we zoom in, we can see many spheres.
Now we've finished the first step.
We can create a constant material, assign it to the actor by selecting Material, and it will apply the material to all the spheres. Next, we need to create an NVIDIA Flex solver component, which requires an NVIDIA graphics card in your computer. For Mac users, this feature may not be available as NVIDIA Flex requires. Next, we need to adjust the parameters here.
First, we change simulation speed to 1.5.
Next, we change particle radius to 0.09.
I won't explain each parameter's effect one by one. Feel free to experiment with them yourself. I'll just quickly make some adjustments here.
Feel free to follow along as I adjust these parameters. We won't be using diffuse particles in this tutorial, so we can ignore them for now. Next, we'll create a keyboard node in CHOP. Then we'll map keys 1 and 2 to the init and start functions in our NVIDIA solver, respectively. This setup will allow convenient resetting and launching. Note, when reopening the project, remember to press key 1 and key 2 to init and start. We can observe the particles falling when emitted because we haven't created collision volumes yet. Then, in SOPs, we'll create a box to serve as our collision volume. We'll also set it to a 16:9 aspect ratio. Since we're working with a flat, planar display here, I'm adjusting the z-axis values. Now let's drag this box into the bounding box SOP. First, we need to enable this option. That completes our collision boundary setup. Now, when we press 1 and 2, we can see the particles flickering, which indicates there were issues with our previous parameter settings.
We've identified that our grid's orientation wasn't set correctly. Since we're working with a flat layout, we need to select the ZX plane. Now when we press 1 and 2 again, we can observe the particles moving normally. Everything looks correct now. The next step is to implement mouse interaction for collision effects.
First, we'll create a force field. Navigate to the force field settings and activate it. Here we can see parameters for intensity and size. Let's first enable fall off, then adjust the size to 2.3.
Next, we'll create a mouse in node, then input left in the left button field to generate mouse click data. When left-clicking, this will output a 0-1 value, which becomes part of our interaction system.
Then add a math operator to your graph for flexible value manipulation. Use its common scope to select which shader parameters it should modulate.
Now, our math node will only affect the tx and ty values.
Next, we'll modify the toRange parameter in the range node from 0 to 7, which will multiply the values by a factor of 7.
We'll map these values to the force's tx and tz parameters. Note that we need to add a negative sign before the tz value to properly align with our visual reference.
We'll now configure the strength parameter. Since our left-right movement already generates force values, we need to combine them with the intensified values triggered by left mouse clicks. First, we'll use a select node to isolate individual parameters, start with ty and tx, followed by the left button input.
We'll first handle the left button values by creating another math node to modify its behavior.
We need to multiply this value by a sufficiently large coefficient to ensure the intensity is visually/physics significant.
Add a lag node to smooth the data stream and prevent abrupt value changes.
Next, we'll process the tx and ty data by creating a math node to combine both channels. Set the Combine Channel node to Average mode to calculate the mean value of tx and ty. Then create another math node, middle-click the previous math node to generate a filter with smoothing effect set to 0.02 and connect it to the subsequent math node. Configure the Combine Chops to Subtract mode, and in Channel Post-Processing, select Positive to ensure only non-negative values are output. Finally, we'll use a math node to connect the left button data with the processed tx/ty values. Set the Combine Chop to Add mode to sum all inputs. Then create a null node and map its output to the strength parameter in the force system to complete the setup.
Now we can observe the expansion effect when pressing the left mouse button. To create an attractor effect, simply input -1 in the math node's multiply parameter. Now observe how pressing the left button generates a converging motion.
Since lateral movement, left-right, currently shows no particle influence, we need to amplify the effect by applying a 100x multiplier to the tx-ty values in the math node.
Now that the physics data is fully processed, we'll proceed to the rendering phase. First, create a camera and set its X rotation to -90 degrees, with translation values X equals 0, Y equals 20, and Z equals 0. This top-down view ensures full scene visibility.
Next, we'll create the lighting setup using an environment light. We'll generate a noise pattern to serve as the light map texture. Then we'll adjust the noise parameters. Okay, now let's drag to the environment map.
Then, in the top network, we'll create a render node to render out the geometry. Then, we'll add a depth node. First, let's modify the render node's resolution to 1920 by 1080 at 32-bit float precision. After that, we'll connect the render output to the depth node. Within the depth node, we'll set the format to 32-bit float, and in the depth space, we chose camera space as well.
Next, to create the water effect, we'll use a plugin. Download the .tox file from the link below this video and drag it into the Touchdesigner network. Connect the depth to the plugin's first input port. In the render settings, assign Environment to Lights and Actor to Geo. Make sure the camera and environment names match mine exactly for proper connections.
Now we can add a null node after it to view the image. Click the blue dot to enable the display background. We can now see the effect appearing.
Currently, it doesn't reach the edges. We could add geometry to improve the effect, but I'll simply extend it out. Just use a box to increase the size and expand the collision volume.
Finally, I'll make some color adjustments and apply post-processing.
First, add a level node. Next, add HSV Adjust node. Then, add a Bloom Effect plugin.
Add another level node.
In the first level node, set brightness to 0.85 and gamma to 0.9. In Bloom, set intensity to 0.7. Add a transform between level and HSV. Set background color alpha to 1 and enable background color.
We can adjust the hue offset in HSV to achieve the desired color tone, and use the final level to modify overall brightness, contrast, etc. Okay, that concludes today's lesson. Thank you for watching. The corresponding plugin link is in the video description below.